So today's video is on an acid-base reaction. So we're going to start off with sort of a review from grade 11, and what I would sort of expect you to know and remember from grade 11. We'll go through a reaction of an acid and a base from that, and then afterwards we're going to turn it into some grade 12 stuff by making the reaction have to deal with weak acids and weak bases. So to start off, we have a neutralization reaction. So you guys should remember from grade 11 that this is a double displacement reaction between an acid and a base, and it produces a salt and water. And what usually happens in this case is that acidic and basic properties are completely destroyed and you end up with a neutral solution. So the common example we gave you last year was hydrogen chloride. A hydrogen chloride or hydrochloric acid plus sodium hydroxide gives you sodium chloride and water. So acid plus base gives you salt plus water. Here's an example of something, another one. So potassium hydroxide and nitric acid, again, gives you potassium nitrate and water. So again, you have water and a salt as your products, and you end up with something close to a pH of 7. So I'm not going to go through this with you. You guys have done titrations last year, and we've done titrations already to calculate some values of K for this unit. So you know that the titration is a lab technique. So I'll let you read through this slide on your own, as well as the next slide on indicators. So hopefully you remember that the indicator is basically used to tell you when to stop doing your titration and move on. So I'll let you sort of go through those, but they're not too important until we actually start doing the labs. So we're going to go through, here's an example from grade 11. So it's a strong acid and strong base titration, giving you salt and water. So what ends up happening is the resulting salt is a neutral, so none of the ions will undergo hydrolysis. So here's an example like I gave you before. It's NaOH plus HCl gives you H₂SO and NaCl. If we eliminate the sodium and the chloride as spectator ions, you get that as your net ionic equation to make your water. And at the equivalence point, there should be exactly enough OH to completely consume all of the H+, with no excess of either. Only NaCl and H₂SO are present in solution, making that pH equal to 7 at the equivalence point. So when we actually go through this, one thing you have to remember, you are never, ever, ever allowed to use C1V1 equals C2V2. We're not allowed to use it when you're doing these types of questions in grade 11, and you are definitely not allowed to use it in any example in grade 12. So please do not use that. So what can you do? You're going to have to use stoichiometry to solve a strong acid with a strong base. So this is just like grade 11. So, first example, what is the molarity of a sulfuric acid solution that requires 35 mils of 1.5 molar sodium hydroxide to neutralize 20 mils of the solution? So there is your reaction that I ever so graciously gave to you this time. Your first step, you have to find the number of moles of H₂SO4 so that you can calculate the concentration. So if I jump ahead for a quick second, in order for you to calculate the concentration of H₂SO4, which is what I'm asking you to find, you need moles over volume. Well, I gave you volume in the question, 20 mils, but I didn't give you moles. So in order for you to be able to do step 2, we have to find the moles of H₂SO4. To find that, you're not given enough information on H₂SO4, but you can find the moles of NaOH and then use some stoichiometry to find the other value. So if we do your moles of NaOH, you should get 1.5 molar times 0.035 liters, and that equals 0.0525 moles of NaOH. Then you can take that and use your stoichiometry to find your moles of H₂SO4. So you're going to convert from moles of NaOH over to moles of H₂SO4. So you have 0.00525 moles of H₂SO4. Here's a quick review on stoichiometry. We want to cancel out, oh sorry, it's not moles of H₂SO4, we just calculated moles of NaOH. So put that up. So we want to cancel moles of NaOH, we put that on the bottom. And we want to keep moles of H₂SO4, we put that on the top. And the numbers we put in are your coefficients from your balanced reaction. 1 and 2. So your moles of H₂SO4 end up being 0.02625 moles H₂SO4. Awesome. Now we can take that number and plug it in here for my N to calculate my final concentration. 0.02625 divided by your liters, which was 20 mils that you started off with. Remember to convert to liters there. Do your quick little division and you get 0.66 molar solution of H₂SO4. So there's your final answer right there. That's grade 11. We are going to use some of these same calculations in grade 12, but what we're going to do now is look at what happens when you have a weak acid and a strong base, or a strong acid and a weak base. So first off, I want to show you this titration curve. Some of you may or may not have done this in grade 11, but basically it shows how the pH changes as you keep adding your base. So initially, if you had your acid, your H₂SO4, you started off with really low pH, and you started to add some base. It would react, and gradually increase your pH. Once all the H₂SO4, or in this graph, the HCl, so once all the acid is reacted with the NaOH, then you add more NaOH and the pH drastically increases because there's no more acid to react with it. Then again, you're going to eventually have so much base left over that it will plateau again at another pH. The equivalence point ends up being about the halfway mark between these two plateaus. Okay, so that's all I'm going to talk to you for now about the titration curve and about the equivalence point. We're going to come back to this later. But basically, it just shows you how the pH changes as you keep adding base to acid, or as you keep adding acid to base, whatever you might be doing. All right, so here's new grade 12 stuff. We're going to look at an example of titrating a weak acid with a strong base, and then in class, we're going to look at an example with a strong acid and a weak base. So for this reaction, we have a weak acid, so we've got formic acid here, or methanoic acid, being titrated with a strong base, sodium hydroxide. So if we look first, see what's going on. Here's the ionization of the acid. So I've got HCOOH and it ionizes, but we know that that doesn't happen very much, okay? So less than 5% of those acid molecules will actually ionize, and we actually have a Ka value because of that. What will actually happen though is because NaOH is a strong base, it's going to say, hey, I don't care if you're a weak acid or a strong acid, I want to react with you. So because again, this guy's very strong, it's going to react with the weak acid completely. So what happens? Again, you're going to split up your ions, okay? So your Na is going to bond with your HCOO- ion to make your salt. And then your H from the acid and your OH from NaOH is going to combine to make your water. So that's your actual neutralization reaction. So that in itself is not really complicated. The complicated part comes from looking at the pH of this equation, because things are going to happen that didn't happen last year in grade 11. So what you have to remember is look at this, one of the products, NaHCOO-. That is a salt. And we already know from our last video that salts can sometimes hydrolyze in water and change the pH of the solution, and that's exactly what's going to happen here. So when we look at this, we know that the sodium ion isn't going to hydrolyze because it's in group 1, but my HCOO- is the anion of a weak acid. Say that right here. And is therefore a base. So the solution will be basic because that ion is going to undergo hydrolysis. Okay, here's my hydrolysis reaction right here. So this guy here is going to accept a proton from water, make my weak acid and an OH. So as you can see, this, even though it's a neutralization reaction, we should still end up with some basic properties. So what is the actual pH going to end up being? You can expect it to be greater than 7, but we actually have to go through and do some more calculations to figure out exactly what it'll be. So that's the difference between grade 11 and grade 12. So let's actually go through an example with some numbers. We're going to use those same two compounds, sodium hydroxide and methanoic acid. So suppose you mix 50 mils of a 0.1 molar NaOH with 50 mils of a 0.1 molar formic acid or methanoic acid. What is the pH of the resulting solution? So first off, I always write out the neutralization reaction so that I know what's happening. And then I realize that this is undergoing hydrolysis, so I need to find what's going on with that. So I need to eventually find the concentration of my NaHCOO minus ion. So before we do that, I just want to backtrack a little bit so that you guys understand what's going on, okay? So we're actually going to add in, let me see, we're going to look at figuring out what was added together. So we're going to look at, we know we're adding NaOH. So how many moles of NaOH are we adding? And this isn't necessary, really. It will be later on, but again, I'm just trying to get you to understand the problem here. So if I do 0.1 molar times 0.05 liters, I have 0.005 moles of NaOH reacting in this solution. How much of my acid do I have? And again, it's my acid, not my ions, just the actual acid. Same thing, C times V. And concentration is 0.1. My volume is 50 mils, which again translates into 0.005 moles. So now when I take a look at those two numbers, and I take a look at my balanced equation, my balanced equation has a 1-to-1 ratio here. So I can kind of make this assumption down here. The same amount of each reagent is going to be mixed, and we don't have an excess or a limiting reagent type question. Okay, so that's going to be important because you will come across some of those later on. So that's how I got my last point there. So now when I'm calculating my sodium hydrogen, my sodium formate or my NaHCOO minus or COO concentration, I'm looking at how much of these are going to actually react. So if I have 0.5 moles or 0.005 moles of this and 0.005 moles of that, I should eventually make 0.005 moles of my salt at the end. And I do, okay? So let's actually look at it. What's the concentration of your NaHCOO salt? So the concentration there, again, it's all a 1-to-1 ratio. So if I do some stoichiometry, I can figure out that I've got 0.005 moles of it because they're all going to react. Now I just have to divide it by my new total volume, which in this case is 50 plus 50, or 100. So my new concentrations of this ion, or of this salt, is going to be 0.05 molar. The other thing you have to consider in this case is that that is a salt, and it will 100% dissociate. So we looked at that in the last example. And what actually ends up happening? If we, so if I go on to the next slide here, hopefully this is okay. When it's dissociated, I know my concentration, sorry, I already did this, NaHCOO is 0.05 molar. Because it's going to dissociate completely, the dissociation is going to look like this. And dissociate completely into Na plus and HCOO minus. Because it dissociates completely, if I have 0.05 moles of this, I have 0.05 moles of this, and 0.05 molar of this. So that means that my concentration of just HCOO minus, after this neutralization has happened, is the same. It's not just 1 0 after the decimal there. So that's going to be really important because I'm going to plug that in later on. All right, now I know, okay, the neutralization reaction has happened, but I'm left with this salt, and I know this salt will hydrolyze, okay? The Na will not hydrolyze, no, but my formate ion over here will hydrolyze. So if I write the hydrolysis reaction for that ion, I look at that, so there's my ion there, and I look at it to see is it going to accept or donate a proton. So again, because it's negative, it's going to accept a proton and act as a base. A proton acceptor is a base. So what do I end up with? HCOOH with that extra H there, and OH minus, okay? I can, again, just like we did in the last video, I can look up the Ka for this acid here, can look up the Ka for that in the back of the text and transfer that into Kb for the base that actually reacted in this hydrolyzation. So I'm not going to go through that because, again, we should have done that in the last video. But, oh, actually, I do have to change this. If you do that, if that's written in your notes, please change it. It's wrong. It should be 5.56 times 10 to the negative 11. So now that I've got that, I can make an ice chart and find my concentration of OH that's left over here and finish off the question. So that's what we're going to do. So again, here's my hydrolysis reaction. I'm not going to worry about any concentrations of water because they don't exist. And I started off from the neutralization reaction with that's my concentration of my ion. And before hydrolysis actually happened, I had nothing in my product side. So this is after neutralization, but before the hydrolysis actually happens. Then we know this is going to go down by x, and these two are both going to go up by x, which leaves me with an x here, 0.05 minus x here. I solved for the Kb for this reaction on the last slide, but if I write out my expression, it's HCOOH times your OH, both of those concentrations, all over the concentration of HCOO minus. If you check your 100 rule, you can eliminate this value of x. So I'm going to do that to simplify everything. So now I'm going to punch in all my numbers. My Kb I calculated, 5.56 times 10 to the negative 11. My HCOOH concentrations and my OH minus concentrations are both x. So I have x squared there, and I have 0.05 on the bottom. Rearrange your equation, isolate for x. Don't forget to take the square root because you do have a square. That's a very common mistake. You should get a value of x of 1.67 times 10 to the negative 6 molar. And that, if you go back to your ice chart, is the same concentration as your OH minus. So from that, you can calculate POH using your negative log formula. And if you do that, you get 5.78. Use that to find your pH, and your final answer should be 8.22. If you look at your answer, it is slightly basic. So then you know that you did it right because you expected a slightly basic solution after this titration. So we're going to stop there, and we're going to do another example in class and clear up any questions that you have then.